This is the second RoPE tutorial that I'm going to give. This time I'm going to concentrate on measuring distances and angles in protein structures. I'm going to quickly go through the initial steps of setting up a project, but a deeper tutorial is already available and I will put the link in the comments. So for this, we're going to choose a new project. So we click Find Project Folder. We choose the beta-lactamase directory, which I've already prepared, and then we can enter a project name. Now we can create the project and begin. We're going to have a look at beta-lactamase. So for this, we will enter a new entity using the UniProt ID code P0AD64. This has managed to pick up the sequence. We're going to give it a name, and then we can create it. Now we can go into the beta-lactamase entity, search the PDB files, and collect a set of PDB codes which match the sequence. We can then set these to download. This will run in the background. If we go from left to right, then we can start to see the files get downloaded and marked as such. I'm going through this very quickly because there is another tutorial which goes into this in more depth. Now from the Protein Entities menu, we can turn all of these files into models by pressing Auto Model from the Toolkit menu. This is going through each of the models and finding the beta-lactamase sequence within the datasets. So now we've ended up with 44 models available, which we can begin to use for refinement. We can prompt RoPE to refine the torsion angles by clicking on RoPE space. And then it will ask us if we want to start the refinement process now. We can press yes, choose a number of threads, and then allow the algorithm to begin refining the structures. Once that's done, then we can save and return to the RoPE space. So what this RoPE space can give us is an indication of which protein structures are similar towards each other. So each of these individual dots represents a PDB chain ID, and when two dots are found close together, this indicates that they have a more similar conformation than those which are far apart. Bear in mind that this is an n-dimensional space, but we can only view 3 axes at a time. The relative weights of the axes can be found here in the Axes menu, showing that the first principal component here has by far the largest weight, but many of the non-displayed axes put together actually has quite a few reasonably important weights within them. One of the useful features of RoPE is that we can actually have a look at the changes which are occurring in the structure along these principal components. So for example, here we want to have a look at what the main changes are in the first principal component. In order to see what the axis directions are, we can take a structure, and if we right-click the structure, then we get a menu in which we can set the structure as a reference point. Now we get 3 axes coming out of the structure with 90-degree angles between them. This is representing the directions and the magnitude of each of the principal components going into this rope space. At the moment, the first principal axis, which has the longest arrow, is actually pointing away from the other structures. In order to make interpretation easier, we can click the arrow. On the web app, you'll need to click the absolute most tip of the arrow, and this gives us a menu. We can reflect the axis, in which case it will point in the opposite direction. It's now facing the rest of the group, including these structures on one side. Now, again, we can click the axis and then choose the Explore Axis button in order to see what this change entails. When we click this, we will see the reference molecule in the background. Axis Explorer will ask you if you want to see the atom motions associated with this torsion angle motion. We usually want to click yes here. What this does is that it does a linear regression of all of the atom positions found in the structures and maps it onto the position found in the rope space so that we can see what motions are associated with the particular direction of torsion angle changes that we've chosen. When we click yes, it might take a while because it needs to load in each of the structures, align the atom positions, and then do a linear regression. Let me talk a little bit through this Axis Explorer. So what we see is the protein structure that we set as a reference. You can see that the chain has changed color in various locations. The level of glow is proportional to the change in the main chain torsion angles associated with each residue. This is calculated as the sum of the squares of all of the contributing torsion angles and should be taken as a relative measurement. On the right-hand side, the legend shows the relative limits of the scale, going from a magnitude of 0 degrees to 3 times the standard deviation calculated. It can be quite helpful to know the actual values, in which case if you press the menu and click Table for Main Chain, then you get these angles listed as a function of the residue number. You can also sort by the angle variation, and if you sort by ascending, then you will see the lowest angles first, and if you sort by descending, then you will see the most variable torsion angles of the backbones of these residues here. It's also possible to copy this list, and we can also export via the menu, either copying the CSV to the clipboard or exporting the CSV as a file. Let's go back to the Axis Explorer. As mentioned before, we can also have a look at the atom position changes associated with this torsion angle motion. We can do this by changing the position of the button on the slider at the bottom. So what this is doing is it's sliding the atom positions along an axis which is equivalent to the axis that we saw on the previous page. So if we move the slider from 0 to -1, then we see the extremes of moving backwards on that axis, and if we move it from 0 to 1, then we're heading to the right-hand side of the plot on the previous page. Note that this is a linear regression of the atom positions, and so you can see that at the extremes we really violate the bond length and angle geometry seen in the structure. And one of the most striking features of this change, which is calculated from the entirety of the structures rather than representing a specific motion from one structure to another, is that the helix at the front here is changing a huge amount when going from one side to the other. So let's have a look at that change a little more carefully. To do this, I'm going to zoom in and find out which of these residues are involved in this motion. To do this, I'm going to zoom in. RoPE generally uses the same principles for zooming as Qt, so to do this, we can right-click and move our mouse backwards and forwards in order to zoom in. In this case, it's easier to see the atoms if we slab differently. So again, with the Qt conventions, if we press and hold the D key on the keyboard, then we're going to see much less of the protein. And we can fiddle around with the alignment of the protein molecule in order to see the loop of interest more easily. There we go. So now we want to have a look at what is changing most severely in this region so that we can have a look and see what the effect of this is across the entire range of protein structures. So in this case, I would say that the backbone of residue 219 and the backbone residue of 214 is exhibiting the most variation here in terms of the distance between the two atoms. Those are the residues which are varying the most aggressively. So now let's use that information and see what the effect of that change is across all of the structures. Let's go back to the Entity menu where we can use this information. So we're going to press the back button twice and now enter the sequence for the entity. Now this is not just a sequence view, but it also allows you to measure distances and angles in protein structures. You can see here at the top that this icon indicates that we're currently measuring distances in the protein structure, but if we were to click it, then we can also measure angles. But for now, let's just focus on measuring distances. Let's go to residue 219 to start measuring this distance. You may notice that the register of these sequences is actually different. This is because in the axis view, what you're looking at is the local sequence numbering for that particular structure, whereas this sequence view is showing us the reference sequence for the entity. So actually, the two residues that we looked at were proline and aspartate, separated by 5 residues. So we can see that the same thing in this sequence is from proline 215 to aspartate 210. If we click on aspartate 210, then we get a list of all of the atoms that have been found for this particular residue. I recommend usually, unless you have a very specific reason not to choose atoms from the main chain. The side chain can vary a lot from one structure to another and is therefore a little bit less reliable for reporting obvious changes in distance. So I usually go with the Ca atom, which is the C alpha atom of the backbone. So if we click this, it will ask you if you're sure that you want to measure a distance from this particular atom. So we click yes, and then we can go to proline, choose the C alpha atom here, and then also click yes. It then proceeds to calculate the distances in the protein structure. This metadata summary screen comes up whenever you have an opportunity to add metadata to the database. We can also now view data according to the individual molecules, and this helps us judge whether the data that we have collected are meaningful. In this case, we have the instance of the protein on the right and the distance measured on the left. And if we flick through, we can see that there is some stark variation in these distances, which matches what we saw in the Axis Explorer. So we can go back and then click Add to Database. Let's return to the RoPE space. Now, as covered in the previous tutorial, we can set a rule that allows us to look at this distance, which has been calculated for every protein chain here, as a color. To do this, we click the Rules button, click New Rule. We want to vary the color, so we choose the final option for the type of rule, and then we want to choose the metadata that we've just generated. So we click the Choose button and then the top choice here. Let's now create that rule, in which case it enters our list, and then press OK. What you can see here is a stark separation between two groups of these structures, where this distance is at the end of one or the other extreme. This is actually associated with the binding of an inhibitor to this protein. So I hope this can help you in your own projects, and happy roping.